Hey everyone, welcome back to Collapsed Latents. This week in AI, your weekly deep dive into the most groundbreaking ideas shaping the future of artificial intelligence. I'm your host, and this week, we're not just watching the AI revolution, we're rewriting the rules. From models that think with images, to graphs seen like art, to a quiet revolution in how we quantize neural networks, this week's papers aren't just updates. They're paradigm shifts. So grab your coffee, hit subscribe, and let's dive into 5 game-changing breakthroughs that are redefining what it means to build smarter, leaner, and more human-like AI. #1. The intelligence crossover, when diffusion models beat GPTs at their own game. Let's start with a quiet revolution in language modeling. For years, autoregressive models, GPT, Llama, Claude, ruled the roost. Predict one token at a time, left to right. Elegant, powerful, but data-hungry. And here's the real bottleneck: we're running out of unique data. Common Crawl still grows, but the best content, code, scientific papers, medical records, isn't being added at the same pace. We're training on trillions of tokens, repeating the same data over and over. So the real constraint isn't compute. It's data efficiency. Enter Diffusion Language Models, or DLMs, and what we're seeing is something profound: the intelligence crossover. In controlled experiments, same model size, same compute, same data. When unique tokens are scarce, DLMs outperform autoregressive models by a wide margin. Not a fluke. Not a one-off. A systematic, repeatable advantage. Why? 3 reasons. First, any-order modeling. AR models are chained to causality. But real-world data, code, math, biology, often has non-causal dependencies. A variable defined later. A term explained in the conclusion. DLMs break the chain. They use bidirectional attention and a diffusion process that lets them model any sequence of tokens in any order. More freedom. More learning. Second, superdense compute. While AR models compute each token once, DLMs refine predictions across multiple denoising steps. That's not just more flops, it's more learning. It's like giving the model a microscope, examining the same data from 100 angles. Third, built-in Monte Carlo augmentation. Every training step corrupts the input at different noise levels. The model learns to denoise from any corrupted state. That's not data augmentation, it's built into the objective. One unique token becomes hundreds of training samples. We tested it, masking inputs in AR models. A small boost, but it saturates. Dropout. Same. Nothing comes close. And the results? A 1.7B DLM trained on just 10 billion unique Python tokens. A realistic data budget outperforms state-of-the-art AR models trained on trillions. A 1B DLM on just 1 billion tokens achieves 56% on HelloSwag, 33% on MMLU, not bad for a small model. And here's the kicker: rising validation loss doesn't mean worse performance. In DLMs, the model keeps improving even after overfitting signs appear, because accuracy depends on relative likelihoods, not absolute NLL. So yes, DLMs cost more compute. But when data is the bottleneck in code, medicine, robotics, that cost is justified. They're not just faster, they're smarter at extracting meaning from every single token. The takeaway: when data is scarce, diffusion models are the new frontier. The intelligence crossover isn't a hypothesis, it's a reality. #2. vThinker, the AI that does just see, it interacts with images. Next up, vThinker, a multimodal reasoning assistant that doesn't just describe images. It interacts with them. For years, AI has been stuck in a loop: describe, hallucinate, drift. But real reasoning isn't passive. It's active. It's sketching, annotating, editing. vThinker flips the script. It's built on a data evolution flywheel, a self-sustaining loop where models generate problems, render images, and build reasoning trajectories, all from scratch. No static datasets. No hand-labeled questions. And here's the magic: the model generates the code to render the image, edit it, and reason through it. Each iteration grows both knowledge and tools, like a living ecosystem of visual reasoning. But quality matters. So they added a coordinated calibration stage. A verifier checks every step. If the answer is wrong but the image is right, a repairer fixes the question. Coherence is enforced. Then comes the visual progressive training curriculum, 2 stages. First, perception alignment. A model learns to localize visual anchors at the pixel level. Where is the peak of this polyline? What's the center of this cube? Then, interactive reasoning alignment. The model generates executable code to draw, shade, highlight, and gets rewarded not just for correct answers, but for correct visual reasoning. It's trained in a sandboxed executor with group relative policy optimization, learning from multiple reasoning paths. And the result? VT-Bench, an expert-verified benchmark where visual interaction is required. vThinker outperforms GPT-4o, Intern VL3, and QN2, 5VL, by 25% on instruction-guided interaction. But the real win? Generalization. Without fine-tuning, it improves 6.3% on math vision, a hard domain. Why? Because visual interaction isn't a niche trick. It's a cognitive scaffold. It makes reasoning more robust, more interpretable. And the models? It evolves. After 5 flywheel iterations, the knowledge system grows 50x, 24,000 nodes across 25 domains. Imagine a geometry problem. The model doesn't just compute the diagonal. It draws the base, adds the vertical, shades the triangle, and uses that visual scaffold to apply the theorem. That's not AI. That's vision-centric thinking, where the image is not a background, but a partner in reasoning. #3. ThinkMorph, the model that thinks in interleaved text and image. Now meet ThinkMorph, the first unified model that doesn't just process text and image in parallel, it interleaves them. ThinkMorph is trained on 24,000 human-curated reasoning traces, tasks like jigsaw assembly, maze navigation, visual search, and chart refocusing. But here's the twist. Each step alternates between text and image, building solutions together. In jigsaw assembly, the model describes a piece, generates a visual reconstruction, and sees mismatches, jagged edges, lighting inconsistencies, then revises. In spatial navigation, it overlays a red path and sees if it hits a wall or loops, then adjusts. In visual search, it doesn't guess, is the pepper red? It zooms in, isolates it, examines the hue. That's not description. That's visual experimentation. And the results? Massive gains. 85% improvement on spatial navigation. 38% on jigsaw. 34.7% average across tasks. But the real breakthrough? Emergent behaviors. First, unseen visual manipulations. The model spontaneously generates zooms, inpainting, motion forecasts, triggered by cues like examine closely. It's using a latent visual toolkit. Second, autonomous mode switching. Despite being trained on interleaved data, it switches to pure text when the visual is redundant, like describing a yellow bus with no window. It knows when to use what. Third, better test time scaling. With best event sampling, ThinkMorph scales more effectively than unimodal models. Why? Because each reasoning chain is a unique trajectory, text-heavy, image-heavy alternating. Diversity beats convergence. On BlinkJ, it gains plus 80% at n equals 8, while unimodal models plateau. This isn't just better accuracy. It's multimodal intelligence in action, spontaneous, adaptive, scalable. The future isn't just multimodal. It's interleaved, interactive, and intelligent. #4. Seeing graphs like humans, the vision model revolution. Now let's shift gears to graphs. You've seen a subway map, a social network, a protein interaction network. And without thinking, you saw the structure, the ring, the hub, the bridge. But AI. Most graph neural networks, GNNs, are like detectives, crawling from node to node, clue by clue. They miss the forest for the trees. So researchers asked, what if we showed the graph like a picture? They took standard graph layouts, force-directed, spectral, and turned them into pixel grids. Then fed them into pre-trained vision models. And the result? Vision models didn't just match GNNs, they surpassed them. On 4 tasks designed to test human-like structural understanding, recognizing archetypes, detecting symmetry, sensing connectivity, finding critical bridges, vision models thrived. And here's the mind-blowing part. On out-of-distribution graphs, larger than anything in training, GNNs collapsed. Vision models. They held steady. Some even improved. Why? Because vision models process graphs globally first. They see the whole structure at once, just like humans. No message passing. No step-by-step crawl. Just render the graph. Let the model look. And the trade-off? Yes, vision models are slower. But the gain in generalization, robustness, and structural understanding is worth it. This isn't just a benchmark win. It's a cognitive renaissance, teaching AI to see like we do. #5. The quantization revolution. Why integer might be better than floating. And finally, the quiet revolution in efficiency, quantization. We've been racing toward low-precision floating-point formats, FP8, FP4, driven by hardware like NVIDIA's Blackwell. But is that the best path? A groundbreaking study says, no. Not for 8-bit. They analyzed blockwise quantization, the real-world standard, and found a crossover point. For 8-bit, MXINT8 beats MXFP8 when the crest factor, max versus RMS activation, drops below 7.55. And in real data, it often does, especially with block sizes of 32. Why? Because with fine-grained quantization, the fixed range of integers becomes more effective. FP's dynamic range advantage is overkill, and the exponent overhead hurts. And the results? MXINT8 wins in QSNR, 40.35 dB versus 31.5 dB, and accuracy. But wait, 4-bit. FP still leads, unless you use outlier mitigation. With Hadamard rotation, the crest factor drops from 2.39 to 2.11, below the crossover point. And NVINT4 not only matches NVFP4, it surpasses it. And training. MXINT8 achieves nearly lossless training, even with fine-grained quantization, once you fix the gradient bias from 2's complement with symmetric clipping. And hardware. INT pipelines are simpler. No exponent comparison, no alignment logic. MXINT8 uses 37% less energy, 21% less area than MXFP8. In mixed formats, 34% less area. This isn't just theory. It's a call to action, to stop assuming FP is always better, to co-design algorithms and hardware for fine-grained integer quantization. Because the future of AI isn't more bits. It's better bits. Hash. So what's the big picture? We're entering an era where data is the bottleneck, not compute. And in that world, diffusion models are the new leaders, not because they're faster, but because they learn deeper from every token. We're moving from vision-assisted reasoning to vision-centric thinking, where models interact with images, not just describe them. We're building interleaved, adaptive reasoning, where text and image aren't just paired, they're co-creators. We're teaching AI to see structure, not by crawling through nodes, but by looking at the whole. And we're rethinking efficiency, not with more precision, but with smarter, leaner, integer-first quantization. This isn't just progress. It's a paradigm shift. The most intelligent AI isn't the fastest. It's the one that learns the most from every single input, whether it's a token, a pixel, a graph, or a weight. So if you're building in code, science, robotics, or low-resource domains, don't just scale up your AR model. Try a DLM. Try vThinker. Try ThinkMorph. Try rendering your graph as an image. Because the future of AI isn't about bigger. It's about better, deeper, and more human-like. Thanks for watching. I'll see you next week when the next breakthrough hits. Until then, keep collapsing the unknown.